Here's an outline of the 11 chapters in the book. We're in the midst right now of chapter 1, which is an introduction. And basically what we do here is we define reliability and we look at the related disciplines such as actuarial science and biostatistics. And then the last thing we're going to do in this chapter is go through this outline of the 11 chapters. So it's very introductory in nature, not much content. Then starting in chapter 2, we look at structure and reliability functions. Those are most useful to a design engineer who is interested in deciding how to arrange the components in a system to maximize the reliability. Then in chapter 3, we look at lifetime distribution representations. Some of those will be familiar, such as the probability density function, cumulative distribution function, etc. Some will be new, for example, the hazard function and the mean residual life function. And then in chapter 4, we look at parametric lifetime models. Some of these will be familiar, like the exponential distribution and perhaps the gamma distribution, but some might be new, like the Weibull distribution, log logistic distribution, log normal distribution, etc. In chapter 5, we look at specialized models, and the 4 specialized models we look at are competing risks, mixtures, accelerated life model, and the proportional hazards model. The last 2 of those models are useful for pulling covariates into the lifetime model, which might affect the time to failure. Chapters 2 through 5 are all about items which fail and are discarded. Chapter 6 looks at items which can be repaired and looks at both the time to failure and the repair time together. Chapters 2 through 6 cover probabilistic models. So it's not a bad idea to draw a line here and say everything above that line is a probability model. Then everything below the line is how to analyze data that you have collected. So that's lifetime data analysis in chapter 7. There is some emphasis in that chapter on censored observations. Chapter 8 is about fitting parametric models to data, such as the exponential or the Weibull or the log logistic. In chapter 9, we deal with the question of how do we pull those covariates that we talked about in chapter 5 into a lifetime model and estimate their effect. If you don't want to go with a parametric model, such as the exponential or Weibull or gamma, then chapter 10 covers non-parametric models. One of the most popular non-parametric models out there is the Kaplan-Meier estimate. Finally, in chapter 11, if we do have a parametric model, we certainly want to assess its adequacy for modeling, and so these are basically goodness of fit tests that can be applied to lifetime data. Starting in chapter 2, we hit structure functions, and structure functions tell you the way that the components are related to one another to form a system. 2 popular types of systems are series systems and parallel systems. Down here at the bottom is something called a reliability block diagram, and this particular reliability block diagram is that of a 3-component series system. This next system right here is a 3-component parallel system. And finally, the last one is neither series nor parallel. You can see there is 1 component at the left, and it is arranged in series with a parallel subsystem of 2 components. So those 3 are examples of reliability block diagrams. We also look into minimal path and minimal cut sets. Then we start to apply probability to all of these notions, and we put together reliability functions which will tell you the probability that an item is functioning at a particular time. And then the last thing, when we have huge systems, sometimes it's useful to put together a reliability bound for the system reliability. In Chapter 3, we look at lifetime distribution representations, and here are 5 of them. The second is probably familiar. That's the probability density function, little f of t. Notice that if you take a first probability course, you probably work quite a bit with the random variables x, and if you have a second random variable, that would be the random variable y. Well, typically, because time is involved with reliability, those are replaced by capital T, and that stands for the time to failure. So the first of these lifetime distribution representations is the survivor function. And the survivor function gives you the probability that the time to failure t exceeds some value lowercase t. Probability density function should be familiar from your first probability class. Then a new one is the hazard function. The hazard function h of t is a measure of the risk associated with an item. So here you see on the right kind of a bathtub-shaped function, and that is typical of a lot of manufactured part where there's kind of an infant mortality at the very, very beginning of the distribution, and then it's flat for a while, and then typically there's wear out on the far right-hand tail of the distribution. This is associated with a survivor function, which from above here is the probability of exceeding a value t. Survivor functions tend to start at 1 and go downwards from there. They are simply 1 minus the cumulative distribution function. Then 2 more are the cumulative hazard function capital H of t, and finally the mean residual life function capital L of t. All 5 of those lifetime distribution functions apply to the various distributions with positive support. Certainly kind of at the center of reliability is the exponential distribution, and the survivor function for the exponential distribution is e to the minus lambda t for t greater than 0. This has a single scale parameter lambda, which is positive, and it is known as the failure rate. This function right here is the survivor function for an exponential random variable. If this product is still working at time 0.5, you can get something which is known as a conditional survivor function, and that's this function right here. The exponential distribution has a very well-known property called the memoryless property, which says if I take this conditional survivor function and just simply slide it to the left, it will have exactly the same shape as the original distribution, which is to say a used item is just as good as a new item. Also, there is a property that says the minimum of exponential lifetimes is exponential, and that applies to both series systems and something we'll see subsequently called competing risks. A second distribution is the Weibull distribution. The survivor function for the Weibull distribution looks like this for t greater than 0. Lambda is known as a scale parameter, and it is positive. Kappa is a shape parameter, and it also is positive. These are 2 of many distributions that are covered in Chapter 4. There is also the gamma, the log normal, the log logistic, the exponential power distribution, the Gompertz, the Macom, all kinds of them, and we'll go over them in Chapter 4. Chapter 5 consists of specialized models that go beyond just an ordinary parametric lifetime model, and the first topic we hit is competing risks. You can think of this hazard function, which is below here, as a competing risk model for a calculator. Your probability of dropping that calculator and having it no longer work is about constant. The risk of that is constant over time. So that's one piece. Then the second piece is manufacturing defects, and manufacturing defects tend to show up early, so the risk is high at the beginning, and then that risk goes down over time. Finally, if you look at the mechanical parts of a calculator, which are the buttons that you press, they are subject to wear-out failures, and those go up with time. So this is a competing risks model for a calculator. Second type of model that we look at are mixtures, and this is where you have, for example, three different factories that might be manufacturing an automobile, and they have slightly different procedures at each of the three factories, which is going to mean you have slightly different reliabilities coming from each of the three factories, but they get mixed together, and so that's a mixture distribution. Now, proportional hazards and accelerated life models, both of those two handle a vector of covariates. So now there is a vector which is usually denoted by Q, and that vector will contain covariates that are associated with a lifetime. Those two models are two different ways of incorporating the values of those covariates into the lifetime model. And finally, the last of the probabilistic models is repairable systems. And in this particular case, if you have 1 being functioning and 0 being failed, you look over the time axis here and you go from the functioning state down to the failed state. And in the failed state, this item gets repaired. Once it's repaired, it's back in the functioning state, and you go up and down in that fashion. There is another function in looking at repairable systems, and that is called the availability. And in this particular case, you can see the availability starts at 1 with a brand new item, and from there it goes downwards and typically hits a steady state value in a well-maintained system. So this completes the probabilistic models. The next chapters handle the statistical methods.